So hi everyone, we're the Journal Club presidents this year. That's Eric, I'm Julia.
I'm Shea.
And if you want, you can pull out your phones. You can scan that to join the email list. You can scan that if you want to sign up to present. And yeah, reach out to us with any questions.
Thank you all for coming today.
Yeah.
Do this now if you want to do it, because we're going to move the screen.
The word?
Which one?
The last one.
So,
Oh, that's what
it's
Alright, we good?
Yeah, just start.
Alright. So I'm Shea, and I'm going to be presenting on research I did this summer. And the project is called the Mission Sun Classifying Solar Flares Using Machine Learning, and it's by me. So first, what is a solar flare? Solar flares are basically just sudden bursts of energy that's released from the sun. And this happens due to something called magnetic reconnection, which basically occurs when magnetic fields on the sun twist or they snap. And that's kind of, you can imagine a rubber band. When you stretch it apart and then you release it, it snaps back. That snapback is just how solar flares are released. Solar flares are really important, but they're also dangerous because they release things called electromagnetic radiation. This radiation, while the sun is really far away from the Earth, it can harm things like radio waves, communication towers, GPS, and power grids. So it can have a lot of dangerous effects on millions of people. So for my research, our goal was to try to use machine learning to be able to predict these solar flares. In the past, solar forecasting relied mostly on just physical models like a simulation or 3D models, but those are really inaccurate and not that reliable. So lately, we've been trying to see how machine learning can be implemented in order to predict and classify solar flares to see how strong they're going to be. For our research, our main goal was to surpass something called Deep Sun, which is a previous machine learning model. The problem with Deep Sun was that it could only tell you when a solar flare would occur, but not how intense the solar flare would be, which is what our goal is going to be for our research. The end result is going to be that we can send a bunch of data into this machine learning model, and then it will output if a solar flare is going to happen and how strong it's going to be. The first thing to know is about solar flares is how they're classified. They're classified simply by how strong they are into 4 different groups. It goes B, C, M, and X, with X being the strongest and B being the lowest. 2 things to know about this is that they're logarithmic, which means that they increase by 10 as you go up. So the C class is 10 times the B class, the M is 10 times the C, and the X is 10 times the M. The second thing to note is that, as you can see in this figure, we have a lot of solar flares that are in class C, but not a lot that are in class X. This is really bad. This is good for us, just in general, because we don't want, obviously, the strongest solar flares occurring often. But for machine learning, it's a very big problem because we want to have a lot of data for a model to be trained on. So with the imbalance of not having a lot of X-class flares, that's something we had to address in this research. So the first thing, and probably the most important thing for machine learning, is having a large data set. And our data set is something called sharp parameters, which is shown on the table to the right. I'm not going to go in depth on what all these parameters mean because it's really complicated. But basically, these are just different characteristics and data that we got from monitoring the sun, such as like magnetic fields or the power of different forces. And we're going to use these characteristics to see what data corresponds to the release of solar flares and what data corresponds to how big and strong the solar flares are going to be. After obtaining all of the solar flare data, we first had to address our first issue, which was the different scaling of all the data. In order to address this, we use something called z-score normalization. And this just makes sure that all the data is on the same scale so that we can compare them equally. It prevents one feature from dominating. Let's say you have a really large number for one data, and all the other data, all the other features are really small. This makes it so they're all equal, and it does this by recentering and rescaling the data so that all the different features are balanced and they're counted as equal. The second thing we have to do is split the data. For machine learning, what you want to do is you want to first train your model and then test how well it works. So we use 75% of our data on training the model, and then the other 25% actually testing how well it worked. This is similar how you have to do your homework, you have to study most of the time, and then at the end you'll actually take a test to see how well you know the information and how much you learned. Before actually testing the data, we had to choose which metrics to use in order to see how well each of our models did, like accuracy. And this came our second issue for class imbalance, which was that if we just trained a model on a regular accuracy, it could just guess that every solar flare would be a C class, since that occurs the most, which isn't good. So we used instead two different accuracies called balanced accuracy, which is BACC, and true skill statistic, which is TSS. BACC just makes sure that each of the solar flare classes contribute equally to the accuracy, instead of just looking at the majority one. It's scaled from 0 to 1, with 1 being the best, and it basically makes it so the models aren't affected by any heavy class imbalance like we have. For TSS, that's another statistic that we use, and it basically measures how much better the model is than if you just randomly guessed what a solar flare would be. So if you randomly guessed that all of the solar flares were just C class, it would be around 65%. So we're trying to make sure our model doesn't do that, and that it can predict all 4 of the classes instead of just the C class. With all that data prepared, we finally were able to test all of our machine learning algorithms. The main ones that we talked about are support vector classifier, decision tree, random forest, gradient booster classifier, and multi-layer perceptron. I'm not going to go deep into what all these algorithms do because we don't have a lot of time, but more for this journal club, we're just going to look at what the results of the models were and how they performed at predicting all of our solar flares. Next, after testing all of the individual models, we then use a thing called ensemble learning. That's pretty simple, where you just combine all of these individual models and you combine them into one model. For example, you could combine a multi-layer perceptron, gradient booster, and random forest, and you combine them into one. And you would do this just to get a better accuracy score, because some models are better at predicting solar flares than others. So you kind of combine their strengths and their weaknesses so that the smaller models will make one large ensemble that's much better. Another thing to note is that we use something called weighted voting. And weighted voting just means that if some of our models in the ensemble are better at predicting solar flares, we're going to weight them higher than the others. So say for this example, if we have MOP, gradient booster, and random forest, for the random forest and gradient booster, we weighted them 2 times higher than MOP, just because they were better at predicting solar flares. Finally, for our results, this is just a table that shows the performance of all the different models. There are a lot more that we tested, but these were our best ones. On the top half, we have the individual models, and then the bottom are our best ensemble models. For the top, the main thing to focus on is gradient booster, which had the best BACC and TSS mean. The mean just means we took the accuracies of all 4 of the classes and we just averaged them together. It had an accuracy of 0.755 for the BACC and 0.510 for TSS, which is pretty good for solar flares. At the bottom, our best ensemble was a combination of MOP, GBC, and RF. That had a BACC of 0.785 and a TSS of 0.569, which is over here. After seeing this initial data, we then created another table that dove more deeply into the individual algorithms and our ensemble. This we just showed the accuracies for all 4 of the classes and not just the mean. The first thing to note for our ensemble is that for X-class flares, it succeeded extremely well at predicting those at 0.912. We were really happy about this because, as we said, we don't have a lot of data for X-class flares. So the fact that our model was able to predict solar flares really well was really exciting due to the class imbalance. The second thing to note is that for RF, by itself, it was really bad at classifying X-class pairs at 0.5 for the BACC and just a straight up 0 for the TSS, which is really bad. But then when you combine it with MOP and GBC, you can see that shot up a lot. And that just shows how strong ensemble learning is and the fact that you can combine a bunch of weak models and then make them really strong. Finally, for confusion matrices, this is another technique that we use to compare our data. What a confusion matrix does is it shows how often the model had a correct prediction or positive prediction versus having a negative or a bad prediction. If you look, you can look at the top left one. You can see that the two labels are actual label and predicted label. For the y-axis, which is the actual label, it shows what the actual flare class was for all of the solar flares. So say for X class, you can see that there's a total of 6 solar flares that were in class X. And then for the predicted label, that shows what our model predicted the solar flare class would be. So for X class, out of the 6 solar flares that were X, it predicted 3 correct, and the other 3 it predicted as M, which is pretty bad. What you would want for a perfect confusion matrix is a diagonal being the only ones with numbers and everything else being 0, because that means all of the classes that our model predicted were correct. Another thing to note for at the bottom left for our ensemble, it was much better at predicting X-class flares, having 5 to 1, which is a lot better, obviously, than RF on its own. The second thing to know is that for SVC, while it had the same success in predicting solar flares for class X, all the others for B, C, and M were really bad. So that's why we didn't use it in our ensemble, even though it boosted the X-class flare prediction, because all the other ones it tanked like really badly. For future directions, there's mainly 2 things that we want to do, probably this year and next year. The first is just getting more solar flare data, because our data consisted only about 5 to 6 years from 2010 and 2016, so it's pretty old. So if we can get new data, maybe to 2020, we can get a much larger data set and a more recent data set. And this will probably help with our class imbalance, because we didn't have a lot of X-class flares to look at. So if we have a lot more data, then obviously we're going to have a lot more data to train our model on. The second thing is just trying new ensemble models, trying new methods or algorithms. This is just like neural networks or maybe deeper models, because the ones that we use were more basic. And that should hopefully boost our model even more. In summary, we started out with questioning how can we teach a machine learning model to not only detect a solar flare, but distinguish between their intensity by classifying it into 4 different classes. We split the research into 3 different parts. The first was preparing the data, which was normalization and splitting the data. Then we actually had to do the experimentation, where we looked at a bunch of different models and tested them using ensemble models as well. And then the final part was the analysis of all the data, looking at all the accuracies and how well they performed using the BACC, TSS, and the confusion matrices. And after all of this, we found that our best model was the combination of multi-layer perceptron, which is MOP, gradient booster classifier, which is GBC, and a random forest, which is RF. These are just contributions. Thanks to the Journal Club staff that helped our CS team, Eric, Lucas, Arjun, and Charlie, and then all of the biology and comp sci teachers for helping out and giving us extra credit. That's it. Any questions?
Sorry, I missed the early part of the presentation. Just wondering, what are the numbers for like for the different classes that you of the solar flare that you're feeding into your system?
The different numbers, like the different data?
Yeah.
I can go back to this. I didn't go into what those were, but they're basically just different.
Oh no, but I mean like for the different classes.
What do you mean?
Like you have 4 different classes, right?
Yeah.
And you're feeding them equally.
Yeah,
in your
equally.
system. But like I was just wondering, what are the numbers of each class that you're feeding?
Like how many we
Yeah.
had?
For each classes.
That was over here.
So when you do this as like when you like kind of do an average of,
Yeah.
of equal weight, wouldn't you put too much like bias towards the? I mean, like wouldn't your data or your program being biased towards like fitting the let's say the X type in this case?
Yeah, so that's why we use the different accuracy scores, the BACC and TSS, because those accounted for the class imbalance. So the accuracy was basically based on each of the 4 classes compared like to
Yeah,
themselves.
but when you put this on equal weights, you then basically those few cases in X will probably blown up in terms of its like contribution to each of your models.
Yeah, they would. But that's what we're looking for because we want to focus on the X classes more. So we were trying to make those accuracies boosted a lot more.
But
Like make our model better.
wouldn't that be like a self-fulfilling prophecy? That because like if you want to fit the X class, you're making a scale that like just magnify the importance of the X class, right?
Yeah.
The scale. So I wonder why you kind of do that in average weighting in that way, as opposed to just doing by, again, just ignore the whole different classes and just kind of by actual numbers.
Because then like our model will basically just count. It'll like primarily just be biased for the C class players. So we had to do something to balance it out. Otherwise, our model would just have terrible accuracies because it would only just say that every solar player is a C class.
Let's prioritize student
Oh,
questions.
yeah,
There's
right.
one back here.
Right.
Oh yeah. Given that like lots of machine learning models rely on like tens of thousands of rows of data, and yours kind of like the largest class only is 552, it looks like. How confident do you feel in your scores, like the scores that you got from testing the data, and how confident would you feel like extrapolating your model to predicting like future data?
I'd say right now I wouldn't use it to actually like predict solar flares, but that's what we're trying to do. Like literally right now we're getting more data that we can use because we only had 5-6 years. So if we can get like 10, 15, that would be a lot better. So I'd say we're like moderately confident. Yeah,
How many features does your model have?
we
What
have
are some,
13
like-
features.
What are some of like the most prominent ones?
Oh, I mean, they're all pretty important. The main ones were, I can go back to here. The main ones would be just the magnetic fields, because that's actually what releases solar flares. So you could focus on that, like how strong or how often magnetic fields, how strong they were. So, yeah.
How did you determine what models to combine for your ensemble?
We just tested a bunch. That's usually like one of the main ways you do it. We had a bunch of different algorithms and we tested all of the combinations and saw which accuracy was the best. Yeah.
Who are you working with?
We're working with professor at NJIT, and then there were also 3 other students.
3
that
other
were with
students.
us.
Was solar flare C the most prevalent because it was the easiest to detect with the machines, or is it actually like just the most prevalent type of solar flare, and why is that?
Oh, you mean for the M class? Yeah, it's just the most prevalent one. It just occurs the most. Yeah.
Why did you choose to study solar flares?
Why did I choose to? Because it was like pretty interesting. It's not just like some boring computer science thing where you're just coding all day. You're actually like having some sort of impact. It's like actually
Okay.
discipline is really important. So I guess that's why. Yeah.
So, if I understand, most of the models predicted have better accuracy for the C or for the B.
I can show you. You talking about this?
Keep going first.
This is the last table. For here?
That graph.
Oh, here, yeah.
So B is the one that is predicted better, or
Um,
I cannot see the letter.
they're all predicted
C.
pretty well. You mean for our ensemble?
Like the higher scores are for what?
The higher scores just means how many solar flares. So obviously for the C class, we're just gonna get a higher number because there's more solar flares to
Just
test on.
because it's-
For X class, we only had 6 to test on. So
Okay, so it's not a percentage.
no.
it's the actual
It's just the
number.
amount of solar flares there were. Yeah, 824.
Thank you. Oh, go ahead.
But yeah, I was just gonna say, if anyone has any questions or wants to present and doesn't know which article to pick, you can reach out to any one of us and we can help you.
Yeah, next week Julia's going to be presenting on introducing the Under Array Telescope at 8 o'clock, the same room next Thursday.
Can I just say something really fast?
Yeah.
This makes me so happy, seeing all of you here. This is the way Journal Club was when I first came to Pingree. With all these students in the room asking questions. This is so awesome. So keep it up.